Hi guys, welcome back to my YouTube channel. Today I'm going to be doing some theory of rates of reactions. So what are we talking about? What is the whole topic about? The basics and what factors can affect the rate of a reaction, right? So when we talk about rates of reactions, like you are reacting to substances, so you have certain reactants, you'll have reactants that will form a certain product. That's the gist of it, right? But there's some sort of minimum requirements, just like when you need to get into school, you need like a certain minimum mark, for instance, to qualify to do a certain course. For reactions to occur, for two substances to react and form a certain product, you have some certain requirements, right? So these requirements are governed by what we call the collision theory. Collision theory basically just says when two substances are made to react, then those substances must have a certain sufficient energy to react. So obviously when substances are made to react, when you're talking about, for instance, your liquid and your gas, then they are in motion, they have a certain kinetic energy. So there's a certain minimum energy that is required from them. And then also they must be able to react in a certain correct orientation. When they collide while they are moving, it must be in a certain correct orientation, right? So this sort of brings in that certain substances will have a certain molecular shape. If you remember VSEPR, so those kind of shapes, your trigonal, planar, tetrahedral, and whatnot. So if you have two substances, also how they collide will, for instance, where the lone pair is located and all that we learn in grade 11 in South Africa. So if you look at the correct orientation, sufficient energy, if these two basic requirements are met, then you can have what we call an effective collision. So when an effective collision occurs, then a product is going to be formed, right? So when you're having a reaction occurring, the substances that are reacting must have a certain minimum energy in order for the reaction to occur, right? So it's called activation energy, which is the minimum energy required for a reaction to occur. Right? So a reaction can either result in a overall release of energy or absorbing of energy, right, during the course of the reaction. So we can use what we call an energy profile to indicate or show whether during the course of the reaction is energy released or is energy absorbed, right? So we can have two types of reactions. We can have let me just jump straight into it. We can have what we call endothermic and exothermic reactions, right? So during an endothermic reaction, energy is absorbed in order for the reaction to occur. During an exothermic reaction, energy is released in order for the reaction to occur, right? So this is called an energy profile, which is used to indicate the course of the reaction and whether energy is absorbed or released, right? So this is your energy. And this is the course of the reaction. Course of reaction. Right. So the reaction will start out with a certain minimum energy, right? So this would be the energy of the reactants. And then a certain amount of energy is required in order for the reaction to occur. So let's say it requires maybe 50 kilojoules per mole, right? So that certain minimum energy that is required is called the activation energy, EA. I'm gonna abbreviate it EA. And then it requires a state of it reaches a state of transition from reactants to products, which is very unstable, which is called the activated complex. Right? And then there is a certain energy of the products after the reaction has been completed and the products are formed. They possess also a certain energy, right? So remember, energy is absorbed in a reaction in order to break the bonds, and then once bonds have been formed, then energy is released. So now the difference between that absorbance and the absorption and release of energy is what determines whether a reaction is endothermic or exothermic, right? For an endothermic reaction, then, or the difference in energy between the product and reactants is called the heat of the reaction, right? So the heat of the reaction is also always energy of the products minus energy of the reactants, right? And then for this one, since it absorbs energy, which means the energy of the products is going to be higher than the energy of the reactants, then delta H is always greater than 0. Or you can say delta H is positive for an endothermic reaction, right? However, for the exothermic reaction, the opposite is happening. Since it's going to have, again, a certain energy of the reactants, which I'm representing at ER, and then this is going to be your activated complex, and then this is going to be energy of the product. This is going to be your activation energy, and this is going to be your delta H, right? Since the energy of the product is less than the energy of the reactants, then your delta H is negative for an exothermic reaction, or delta H is less than 0, right? So you can represent the reaction, the energy required in a reaction, and the energy released, energy absorbed. For instance, this is energy absorbed, energy released. You can represent it using the energy profile, right? And then you can be able to get whether the reaction is exothermic or endothermic. This is usually given to you. It is not affected by the factors, the temperature, any external factors, by the state of division or concentration. It's standard, constant for a specific type of reaction, right? The delta H, that is. So it's usually given to you, and you can then be able to see whether you have an endo-exo reaction depending on the positive value or the negative value of delta H, right? So in a reaction, you can also be able to represent the course of the reaction using the Maxwell-Boltzmann curve. Maxwell-Boltzmann curve, right? So in this curve, you're going to have number of particles, and you're also going to have the kinetic energy of those particles in the x-axis, right? So as the reaction occurs, you sort of have some of the particles are able to form or to react in an effective way. So there's effective collisions to form the product, and some are not, right? So you'll find that generally in a reaction, there'll be sort of a certain average kinetic energy that most of the particles have. So you get the bell shape from the number of particles that are there and which of those particles were able to form the effective collisions, right? So from this, you can say, for instance, you have your activation energy, your minimum energy required. Let's say it's around here. Then what this means, or from this graph, you can be able to say that all the particles that come after the activation energy are the particles that are going to form the effective collisions. So my shaded area is the particles that were able to form or have the effective collisions, right? And form the product. And then these particles did not have the minimum energy required for the reaction to occur, right? So when you have these reactions, they can be affected, or the rate of the reactions, how fast or slow the reaction is occurring, can be affected or changed by certain factors, right? So we deal with 5 main factors, and there's a 6th factor which I won't really focus on, but I will mention, right? So there's what we call factors affecting the rate of a reaction. The first one that I'm going to speak about is temperature. Right? What does temperature do? If I have a reaction, for instance, let's say it's zinc and HCl to form zinc chloride and hydrogen gas. Right? If I increase the temperature, what's going to happen? Then the particles that you have in solution are going to be moving at a higher kinetic energy, or at a faster speed, which means they're going to have a higher kinetic energy, right? So the temperature, it can be used, increase in temperature can be used to affect or increase the rate of a reaction that has solid, liquid, gas, or aqueous states, right? For all the states, when you increase the temperature, then the kinetic energy of the particles increases, right? So what it does is it increases the average kinetic energy of particles. So if you refer back to what I said measures minimum requirement of the success of a reaction, we said we must have a certain specific sufficient energy and a certain collision in the correct orientation, and you're going to have what we call effective collisions, right? So if I increase the average kinetic energy of particles by increasing the temperature, right, then what happens is that there'll be more particles with sufficient energy, right? And then you're going to have more effective collisions per unit time. Remember, I forgot to give you the definition for rate of reaction. It's the change in concentration of the reactants or products per unit time, right? So if I have more effective collisions per unit time, then I'm going to have a faster reaction than before, right? So now if you look at this graph, the Maxwell-Boltzmann curve, what happens to the graph, the shape of the graph, when I increase the temperature, right? So I'm going to draw two graphs for you. This is called as T1, T2, right? So we said when we increase the temperature, then you have more particles with a higher kinetic energy than before. That's why we said we increase the average kinetic energy of the particles. So between T1 and T2, which one would you think is representing the higher temperature, right? That's going to be T2. So T2 is higher than T1. Higher temperature, if you look, it's now particles meeting the minimum energy required. There's now more. It's now the red and the blue shaded area. And also the graph, the peak of the graph, you must also decrease. It must also decrease because you are having less particles having a low kinetic energy. It sort of shifts to the right, and the particles with a lower kinetic energy would have been reduced in the solution or in the reaction, right? So that's how temperature would affect the Maxwell-Boltzmann curve. And then you have to look at other factors as well. So I said I'm going to look at 5. Another factor that will affect the rate of the reaction would be concentration. Now, concentration can apply to a reactant that is an aqueous solution, right? Which means it's a substance dissolved, a certain solute dissolved in a certain solvent, right? So like for instance, if you take salt, you put it in water, then you have an aqueous solution. You don't have liquid, you have an aqueous solution. So the concentration applies to aqueous solutions, and it can also apply to gases, but we mostly deal with the gases, right? So when you have an increase in concentration, what is the concentration? That the definition for concentration is the amount of solute per liter of solution, right? So if I increase the concentration, let's say I had a certain 1 liter and it had a certain number of particles in the solution, right? If I increase the concentration, then now I have more in the same amount of solvent, I have more particles in the solution. So higher number of moles in the solution, right? So now the question becomes, how does that affect the rate of the reaction, right? So if again you're having more particles per unit volume, increase in concentration, increase number of particles per unit volume, then you want to have more effective collisions per unit time, which means you're going to have a higher reaction rate, right? So for instance, if you look at this one, we had zinc, which was a solid, we had HCl, which was an aqueous solution. If I was to increase the concentration of this HCl, let's say from 0.5 mole per decimeters cubed to 1 mole per decimeters cubed, then I would have doubled the rate of the reaction, right? Which means then the concentration can be able to alter the rate of the reaction. But it also is important whether the concentration that you are changing is it of the limiting or the excess reagent, right? So if, for instance, you are increasing the concentration of a excess reagent, then it's going to increase the rate of the reaction, but it's not going to increase the amount that you're going to produce, right? Because it's already in excess. But if you're increasing the concentration of a limiting reagent, then it's going to increase the rate of the reaction and the amount that you produce, since you're now going to have more number of moles available to react, right? So you have to also be aware of that, which I'm going to bring in back when we are doing questions. And then another factor that can affect the rate of a reaction is pressure. Now, pressure affects the gases, right? So if I increase or decrease the pressure, I can do that in order for me to increase or decrease the rate of the reaction. So how can I increase the pressure? I can increase pressure, I'm going to call it P, by decreasing volume. So if I had a certain amount of gas in a 1 liter container and I put the same amount of gas in a 0.25 liter container, then I would have increased the pressure, right? Then I'll keep the same number of moles occupying a smaller volume, which means since I have increased the pressure, then what is happening is the particles are closer together. Right? And then more effective collisions per unit time. And then you also have a higher reaction rate, or the reaction rate increases, right? So pressure is referred to when we have gases as your reactants, so you can increase the rate of the reaction. So another thing to mention is I'm referring to reactions that are not reversible here. So these are reactions that are not reversible reactions. These are just one-way reactions that reach completion. So you can see I was using a single arrow for my reactions, right? Let's say we had a reaction. This is usually in equilibrium, but for just to help you to understand the concept, I'm going to write it as an irreversible reaction. So let's say you have this formation of ammonia, and these are gases. Nitrogen is a gas, ammonia is a gas, hydrogen is a gas. So let's say you're having this reaction and you want to increase the rate of the reaction. You can have the same amount of gas and just put it in or decrease the container, right? Decrease the container. You can use a pistol to decrease the container that it's occupying. Pistol is something like this. So if I press it down, then I decrease the volume, right? And then what happens is that the pressure increases and the rate of the reaction also increases. Another factor that affects the rate of the reaction is the state of division, or you can call it surface area. This applies to solids, right? So when you have a solid, if you are using, for instance, powder, always refer to powder versus granules, right? So if you're using powder, then you have a larger surface area compared to granules. So when you use powder instead of granules, then the rate of the reaction is going to be higher for the same mass, right? So let's say in that same reaction, zinc plus HCl, for the zinc, you decided to, in one reaction, use powder, and the other reaction, you use your granules. The one with the powder should have a higher reaction rate, right? So powder versus granules. The powder is going to have a higher reaction rate. It has a greater surface area, so it's going to have more points of contact for reaction to occur. Right? More effective collisions per unit time, and a higher rate of reaction. Right? And then number 5, we're going to speak about the catalyst. So what does a catalyst do to the rate of the reaction? You can either have a negative catalyst or positive catalyst. A negative catalyst decreases the rate of the reaction. Positive catalyst increases the rate of the reaction, right? Increases the rate of the reaction. How does it do that? So you can imagine, let's say you were going to watch a soccer match or football, and the tickets were selling for 100 rands, right? You get there, tickets are selling for 100 rands, and then they realize that there's like 10 minutes before the match starts, there's not a lot of tickets that have been bought. So they decide, you know what, let's just lower the price so that more people can be able to afford the tickets, right? So let's say you had 60 rands. Now, initially the tickets were 100 rands, which means only people who have 100 rands could enter the venue. But now that the tickets are 60 rands, it means even you, with your 60 rands, you can be able to enter the venue, right? Which means since the bar has been lowered, there's more people who can come in. It doesn't mean that those who were inside are going out or anything changes with those who had 100 rands. They also stay in, but more people are able to come in, right? That's what a catalyst does. It lowers the activation energy so that more particles can meet the minimum requirements for the reaction to occur, right? Remember we spoke about activation energy. So what it does is it lowers the activation energy, so it offers an alternative pathway for the reaction to occur, right? So what a positive catalyst is going to do is lower the activation energy, right? Which means more particles will have sufficient energy, right? And then that means there's going to be more effective collisions per unit time and a higher rate of reaction, right? So from those graphs that we have done, let's look back at this one. What would a catalyst do? So remember I had put in the activation energy as, let's say it was around here for the reaction. If I was to introduce a catalyst, what it's going to do is lower the activation energy. So let's say if my activation energy was 50 or 100 kilojoules, it's now 60 kilojoules. So it lowers the activation energy. So this now becomes, blue becomes without catalyst and red with catalyst. So since it's lowered the effective, or rather the activation energy, then you can see my blue area, I'm going to have more particles. And also I'm just going to have more particles overall, right? That have the minimum energy required. And how does the catalyst, or the effect of the catalyst, how can it be shown in the energy profile, in the questions that we're going to do? So in the energy profile, you can see the effect of a catalyst. We said it lowers the activation energy. This was activation energy, right? Difference in energy between the activated complex and the energy of the reactants. So what it's going to do is lower the activation energy. So the red would be with catalyst and the blue would be without catalyst, right? Same thing here, it's going to lower the activation energy, which means that the catalyst does not affect delta H. It only affects the activation energy of the activated complex, right? So that's an important thing to know. It does not change delta H, right? It only changes the energy of the activated complex and the activation energy. And then the other factor, the sixth factor, is the nature of the reactant that you are using. So for instance, if you are having your metals using zinc instead of copper, using nickel instead of copper, using another metal, can affect the rate of your reaction, right? So that one we don't really focus on a lot, but it's also a factor that affects the rate of the reaction, the nature of the reactant that you are using, right? I hope that was very helpful. I'm going to now do another video where I do questions so that you can use them for revision and you can be able to engage a bit more with the content and apply it, right? So if you have any questions, just drop them down below. And please like the video, please subscribe. Thank you for tuning in. I hope it was really, really helpful to you and you understood the topic a bit better. See you on the next video.